Hello, my name is Jonas Tjomsland, and on behalf of myself, Sinan, Kalkan, and Hatice, I would like to present our work on continually learning social appropriateness of robot actions. As we all know, robots' role in society is steadily increasing. In the picture on the right-hand side here, we see a potential future scenario in a home environment where a domestic robot is trying to determine whether it is appropriate to start vacuum cleaning when observing this social situation or social context. We see that someone is laying on the sofa, maybe sleeping, there's children there, and it is difficult for the robots to determine whether it is appropriate to start with this action. Achieving such appropriate social behavior is not trivial, not even for humans. However, as humans, we have the ability to recognize social contexts and can link a social context to what actions that are appropriate to do in that context. We also have the ability to continuously learn from our observations and update our knowledge when faced with new social contexts and feedback about the appropriateness of actions. In our work, we approach the challenge of giving robots the same ability. We present two main contributions. We have created and labeled through crowd labeling a dataset of social appropriate labels for domestic robot actions in a home scenario. Using this dataset, we propose a Bayesian continual learning framework using existing continual learning methods to allow the model to continuously update its knowledge without forgetting previous experiences. The dataset is created in Unity. We simulated 1,000 different social contexts and looked at 29 features, such as, is music playing? Is there a group in the room? Is there someone on the sofa? Is there animals, children? We also investigate then 16 robots' actions and the social appropriateness of them. In such a social context, is it appropriate to do these 16 set of actions? To label the appropriateness of these actions, we used the crowdsourcing platform from Prolific. We were able to label 1,000 different scenes, where we asked annotators to indicate on a scale from 1 to 5, where 1 deemed as very inappropriate and 5 indicated very appropriate, the social appropriateness of the 16 robot actions when viewing the scene. We collected 15 different judgments per scene, and we also asked annotators to give a reason for why they answered as they did. These are the actions we have looked at. As you can see, we look at 16 actions, but many of them are the same, executed in different ways. We look at vacuum cleaning, mopping the floor, carry warm food, carry cold food, carry drinks, carry big objects, carry small objects, cleaning, and starting conversation, separated into two different groups of whether the action is executed within a circle or in the direction of an arrow. These actions were chosen because they vary in intrusiveness and they also are relevant for a home scenario and a domestic robot. The continual learning approach we use is an extension of Appropriateness et al.'s work on uncertainty-guided continual learning with Bayesian neural networks. Basically, Appropriateness et al.'s method utilizes the inherent uncertainty in the weights of a Bayesian neural network to tune the per parameter learning rate such that parameters or learning weights that are important for previous knowledge are updated less when new knowledge arrives or new data arrives. Using this method, we propose 3 different models. We have a baseline with no continual learning. We have a 2 tasks model, which separates the 16 tasks in 2 groups. So it first trains on the 8 first actions and learns the social appropriateness of those actions, given different social contexts, before receiving data for the next 8 actions and doing the same. Finally, we have a 16 tasks model that learns the social appropriateness for each of the 16 actions incrementally. If we take a look at the data from the dataset, we can provide some interesting insight. For example, when looking at features as number of people in the room, number of people in a group, whether the robot is within a group or whether the robot is facing a group, we see that intrusive actions such as vacuum cleaning, mopping the floor, or carry big objects show a negative correlation relationship with social appropriateness, meaning that it's deemed less appropriate to do these actions when there's a lot of people in the room, the robot is standing within the group, or when the robot is facing the group. They're basically deemed too intrusive for that. On the other hand, actions like starting conversation is deemed to be appropriate when the robot is standing within the group or when the robot is facing a group. We also see that the distance to the group is relevant for the appropriateness of the different actions, that it is less appropriate to start a conversation if the robot is far from a group, and it's more appropriate to start to do intrusive actions when the robot is far from a group. We could look further into the distance features and see the same relationship here. If you look at distance to the closest human, distance to the second closest human, or distance to the third closest human, we see that the intrusive actions are deemed to be more appropriate when executed further away. On the other hand, starting conversation is deemed less appropriate as the distance from the people or the humans are increasing. Let's take a look at the results. What you see here is the training process, the continual learning process for the 16-task model. So we plot the loss on each action as the root mean squared error between the predicted appropriateness label and the actual average appropriateness label given from the annotators. And what we see is that when an action is trained on, a task, as we call it, the loss drops for that action and it stays low throughout the continual learning process, meaning that the catastrophic forgetting, basically making sure we don't forget previous knowledge or how socially appropriate actions we previously trained on is successful and satisfactory. We also report average root mean square error on the entire test set for the 16-task model of 0.63. So this is the root mean squared error between the predicted appropriateness labels from the model and the actual average appropriateness label from the annotators. So remember, from a scale from 1 to 5, 0.63 is quite satisfactory. Let's also take a look at the test scene from the unseen data in the test set. What you see here is a social context in the living room where the robot is standing within a group of people quite close to all the people around it. We also see an animal in the room and someone standing on the other side of the sofa. Below in the table, we see the actual label provided by the annotators, average over 15 annotators for this scene, along with the predictions from the 3 different models, our baseline model, the 2 tasks model, and the 16-task model. We see similar behavior or information as in the correlation tables. For example, intrusive actions such as vacuum cleaning, mopping the floor, or carrying big objects are both predicted and labeled by the annotators to be quite inappropriate in this scenario and this social context. On the other hand, starting a conversation when the robot is standing so close to the people within the group and facing the closest human are deemed appropriate both by the models and the annotators. To conclude, we presented a data set where we explore the social appropriateness of our domestic robots' actions. This data set provides new insight in appropriate behavior for socially interactive robots in a home scenario. Using the data set, we present a Bayesian continual learning framework which models socially appropriate robot behavior and allows it to continuously update its knowledge about social appropriateness and social appropriate actions without forgetting what it already knows. Thank you.